1.1 functions. A function is a relation in which each x goes with one y. I think that's kind of a difficult definition to understand, but each x goes with one y. I think that the first example illustrates it pretty well. All right. The second one is not a function. And you can tell because this specific x splits and goes to two different y values. The definition says each x has to go to exactly one y. All right. And basically what that means is if you took an equation and plugged in 6 and you got 8 as your answer and it was right, and then I plugged in 6 and got 10 and it was right, that can't possibly happen. You can't plug in, you plug in a number, you're going to get one answer, and I'm going to get the same thing. All right, so that's a problem. That's not a function. This one's good. This one's a function. So each x goes to one y function. These examples down here are a little bit harder to see. I think it's easiest to see the ones that aren't functions. All right, so if you notice set p, if you plug in -4 and get 3, and then I come in and plug in -4 and get -3, that's a problem. That one's not a function. The other two are, and I guess it's easiest to see when these numbers, when the x numbers are all different, there's not going to be a problem. That's a function. Each x is only going to give you one possible y answer. This one, when these x numbers are all different, yeah, each x is going to give you a y answer. That's a function. The domain is the set of all possible, I'm going to say, inputs. Whatever you plug in. Okay, that's a better answer than the x variable. It's usually the x variable, and that's probably what you learned in the past. The domain was the x numbers. But what if you're looking at an equation that says r equals 3s plus 5? There's no x numbers. All right, so it's not always the x numbers. It's always the input numbers, or we could call it the independent variable. It's always the independent variable, the input, the one you plug in. The range is the set of all possible outputs. We remember the y variable, but it's not always going to be a y variable. It's whatever comes out, and that's called the dependent variable. I like to visualize. Visualize yourself holding a calculator. Right? Whatever you can possibly plug into that calculator would be the inputs. Those would be the domains. Okay? Whatever the calculator's answer spits back at you, the output, that's the range. What goes in is the domain. What goes out is the range. Okay? So, if you think about an absurd example, your input on your calculator could be a number 1, or it could be a number 7, or it could be the x squared button, or whatever. There's a lot of different things you could push on a calculator, but there's probably not an eject button, right? Eject wouldn't be part of your calculator's domain because that's not one of the inputs. Okay. An easy way to tell if a graph is a function is by the vertical line test. Vertical line test, I know you've done that before. So, when you look at the graph, you look at this graph and you can see that that is a function because it passes the vertical line test. And you can see that this one down here is not a function because it does not pass the vertical line test. And what I mean by that is the vertical line hits that graph twice. Okay, when it hits the graph twice, it's the same thing as that x number hitting two different y numbers. All right, the x number is hitting two different y numbers. For instance, this corresponds with the x number of 3. 3 splits and hits one time up here and one time down here. That's not a function. All right, so give the domain and range and tell if it's a function. Well, let's do it backwards. All these are different, so that's a function. Domain, I'll just put D colon, all right. Domain is the x numbers, so we all remember that, -4, comma, -1, comma, 1, comma, 3. And the range is the y numbers, excuse me, -2, comma, 0, 2, and 5. So then let's do the one directly underneath. We can see the x numbers are all different. That means this one is a function. And the domain is going to be the x numbers, -3, 0, 3, and 5. It doesn't really matter if you write them in order, but that's usually what you'll see. The range would be the y numbers, and there's only one range, and that's 5. And that's fine. That's okay. That's like if you had a mapping and -3 went to 5 and 0 went to 5 and 3 went to 5 and 5 went to, everything goes to 5. That's fine. That's still a function. That's still a function. Okay. So then once we look at the graphs, that's when I start talking about smashing the function. Okay. And you look at that parabola and you're supposed to notice that it goes on forever. Okay. And so if you smash the function and only look at the x numbers, okay, visualize, you've got a plate here and you've got a plate here, and they kind of smash it together. That's the way I look at it, all right? And if they smash that function onto the x-axis, everything gets covered, all right? Everything gets covered. All x's would get covered. So you can say all real numbers if you want, but a lot of the times in this class, you're going to have to write it in interval notation, which means from -infinity to +infinity. All right, that means all real numbers. That's this symbol right here, all real numbers, or -infinity to +infinity. Notice the parentheses. Parentheses around that interval does not mean that that's an ordered pair. It means we don't include infinity. You can't equal infinity. All right. For the range, I know I'm getting messy here. For the range, I'm going to squish it onto y. I'm only going to look at the y numbers. And you can see that that thing tops out here at +4, but it goes on forever down to -infinity. That would be -infinity down there. And so this range, we typically write it from least to greatest. It goes from a low number of -infinity to a high number of +4, and then we use a bracket to show that it could equal that 4. All right, bracket indicates we could equal the number. Parentheses indicates we will not will not equal that number. So the oval down there is not a function. Again, I would encourage you to think about squashing it. If you squash it and only look at the x numbers, it appears to go between -5 and 5. The x numbers are going to go between -5 and 5. So this domain will be bracket -5, comma 5 bracket. And that just means all the numbers in between and including -5 to +5. If you look at the range, just look at the y numbers that are covered. Okay, and again, I visualize squishing it onto the y-axis. It appears that those numbers are going to be in between what and what? -3 and 3. Correct. including, so bracket. All right, any questions? All right, draw a quick sketch. I'm not too concerned about your graphing abilities right now. We could use Desmos for this. I don't really care. I'm gonna try to save time by drawing the graphs quickly. So don't worry about if you didn't know what this thing looked like. Assume I used Desmos or whatever. Okay, so 2x minus 5, a y-intercept of -5, up 2 over 1, up 2 over 1. You guys should know how to draw slope-intercept form. All right, so we've got that graph. That's the graph. Is it a function? Well, vertical line test tells me, yes, it is a function. Each x number hits once. Those vertical lines are x numbers. All right, they're x numbers. And so, yes, this passes the vertical line test. So, yes, this is a function. Give the domain and the range. Well, the domain is, if you squish this thing onto the x number, or onto the x-axis, it's going to cover everything. And so the domain is going to be all real numbers, or we can write it like that. Again, parentheses mean we can't equal infinity. We can't ever get there. The range, if you squash this blue graph onto the y-axis, it's going to cover everything on the y-axis. So the range is the same thing. The range is also all real numbers, -infinity to +infinity. So then the next one, x squared plus 3. You should know that x squared is a parabola. And that's just something you should probably know. Plus 3 shifts it up 3. So we're going to have a parabola. I'm just drawing a kind of a quick sketch. That's not super accurate, but it's pretty good. It's a parabola that's shifted up 3. The vertex is at 3. All right. That's good enough to tell me that it is a function. Vertical line test, only going to hit one time. And if you squish it onto the x, you're covering everything. So domain is all real numbers. Range is not going to hit everything, though. Range is not going to hit everything. It's only going to hit from this 3 and up. It's going to hit from 3 to infinity, from 3 and up, from 3 to infinity. The range is bracket 3 to infinity, parentheses, meaning we can equal 3, but we can't equal infinity. Now, these two are the ones you probably don't know what they look like. X equals absolute value. You might know an absolute value is a V shape, but this one's actually sideways. So this one's kind of weird. You've probably never graphed this before. It's not a big deal that you didn't know what that looked like. But think about your vertical line test. Is that going to be a function? That's not a function. Not a function. Then if you look at your domain and range, for domain, I visualize squishing it onto the x. I cover this. So the domain is from 0 to infinity. For the range, squish it onto the y and everything gets covered. If you squish that thing onto the y and everything gets covered, that means all real numbers again. All right, we see that kind of a lot. The range is going to be from -infinity to +infinity. Now the next one's a really weird one. And I know you've graphed those before in Algebra 2 class, but you probably don't remember. It's going to have an asymptote. Specifically, it's going to have an asymptote at -2, because if x were -2, you'd have a 0 on the bottom of a fraction. 0 on the bottom of a fraction is going to be bad news. So you've got something called an asymptote right here at -2. Go ahead and draw a vertical dotted line through x equals -2. And then without going into it, I don't know, you could plug in numbers to figure this out. But if I plug in -1, I'm going to get +3. And if I plug in +1, I'm going to get positive 1. You're going to have something that looks like this. And likewise, you're going to have this and this. So it's not super important that you're super accurate. It just doesn't ever cross or touch that vertical asymptote, and it doesn't ever cross or touch the zero, the x-axis. All right. I call it a double boomerang or a double banana graph. All right. But like as far as is this a function, draw your vertical lines through. Your vertical lines are only going to hit one time. Once. So is this a function? Yeah, this is a function. Weird, but it's a function. And then as for your domain and your range, this is going to do something super weird. Because if you squash that thing down, it's not going to cover the entire graph. Because it's not going to cover right here where this asymptote was. It's going to cover everything else, though. It's going to cover everything else. So all real numbers except -2 would be the English language way of saying it. All real numbers except for that point at -2. How we would write this could be like this. We would say from -infinity to -2, but not including. So parentheses. And then we would put a U, a capital U stands for union. Union means join. Unioned with from -2 to positive infinity. I know that's kind of weird. It'd be easier if we could just say all real numbers except -2. And that's what that means. All right, so the range, if we squash it onto the y-axis, it's going to cover pretty much everything except it's not going to hit that number 0 right there. It's going to cover everything except 0. All real numbers except 0. All real numbers except 0. So your range is going to be from -infinity to 0, but not including, unioned with 0 to positive infinity. I know that's tricky, okay? I know that's tricky, but that is what it is. Okay. Number 4 feels more comfortable. Evaluate. The word evaluate literally means find the value. Usually that means plug a number in. Okay. Evaluate each function. So when this says f of 5, they're just saying plug in 5. Now, you're free to use a calculator if you need to. Okay. Be careful here. Don't write this down. Okay. What a lot of people will do is they will start and they will basically copy the problem and plug in the 5. -5 squared minus 6 times 5 plus 4. All right, they plug that in. But here's where a lot of people mess up, and some calculators mess up too. We're not squaring -5. We're not plugging in -5. We're not working with -5. We're working with +5. All right, so you have to square the 5, not square the -5. And so if you're using a calculator, what I would recommend you do is every time you plug a number in, put it in parentheses. If you put that number in parentheses every time, then your calculator is probably going to get it right. If you don't put it in parentheses every time, then some calculators will get it right and some calculators will get it wrong because they all kind of handle order of operations a little bit differently. But what I would do on this problem if I were you is I'd just do that first step in my head, okay? The first step in my head, if I'm going to square the number, I'm plugging in 5, I'm going to square a 5, that's 25. It just so happens that it's going to have a negative in front of it. That's going to be -25. And then minus 6 times 5, that's minus 30, plus 4. If you can get this far, then you're going to get it right. That's -55 plus 4 is -51. I make a big deal out of that problem. It doesn't seem very difficult, but I make a big deal out of it because a lot of people will miss that. You got to be really, really careful with negative x squared. Really careful. F of b, this just means you're plugging in b, and that's not gonna, you're not gonna do much there. Negative b squared minus 6b plus 4. I apologize, my 6's and my lowercase b's look an awful lot alike. Try really hard to make them different. And then the last one, notice it says g of negative 4, so you're plugging in a negative 4 right here. It's 3 times negative 4 plus 1, all right? As long as, when you're using your calculator, as long as whatever you plug in, you put in parentheses, you're probably going to be okay. That is negative 12 plus 1, that is negative 11, there we go. Evaluate. Ironically, number 5 is easier to do to the number 4, but more people will miss it because it seems confusing, right? You don't quite understand what you're doing. But finding f of 0 just means that's the x number. The x number is 0, so they're saying, give me the y number, okay? What's y? What's y, question mark? That's another way of asking the question. What's y? So when x is 0, y is 8, right? This answer is going to be 8. So I would probably write it as f of 0 equals 8. That's not supposed to be tricky, but I know it can be confusing at times. You know, find the y when x is 0, all right? Now people really screw up on this graph. When they're looking at the graph, they don't understand what f of 0 means. F of 0 on this graph, well, just think about it as that's the x number, okay? When x is 0, what's y? When x is 0, what's y? So you have to look specifically on the graph where x is 0. X is 0 right there. That corresponds to this point on the graph. The point is 0, 2. So the question says, when x is 0, what's y? Well, what is the y then? It's 2, right? When x is 0, y is 2. F of 0 equals 2. Students really struggle with that one. And then the next one is a mapping. That's not that bad. When x is 0, y is 4. F of 0 equals 4. Number 6, last slide. Determine the intervals over which the function is increasing, decreasing, and constant. So increasing, decreasing, and constant, it's basically talking about part of the domain. I think it's fairly simple to see where this graph is increasing. You're looking right here. Okay? That's the part of the graph that's increasing, correct? So what I want you to do is squash that part and just look at the domain for that. If you only look at the domain for that, you're looking from negative infinity to negative 1. And we're going to use a bracket. It's increasing from negative infinity to positive 1. Do you guys see that? So then decreasing, again, most people are pretty good at looking at the graph and saying, well, this is the part of the graph that's decreasing. That's decreasing. But you need to really just look at the x numbers. I don't care about that. I don't. What people will do is they'll say it decreases from 2 to negative 2. But I don't want to do that. I don't want to look at the y numbers. I have to look at the x numbers. I have to look at the domain. So don't look at the x, or don't look at the y numbers. Look at the x numbers. It decreases over this interval, and that's from negative 1 to positive 1. So decreasing from negative 1 to positive 1. And then it's constant, and yeah, we can see it's constant right here. But look at the x numbers. Look at the domain. We're talking about the domain. So that's right here. That's from positive 1 to infinity, from positive 1 to infinity, like that. Increasing, decreasing, constant. We're talking about domain. By the way, if I asked you what the domain of that is, you squash the whole thing, it covers the entire x-axis. That means the domain would be all real numbers. If I asked you what the range for that function was, just squash the whole thing. It goes from 2 down, from positive 2 at the top to all the way down to negative infinity. So we say from negative infinity to positive 2. Number 7, increasing. Increasing, well, that's here. I don't care about the 3,000. Don't look at 3,000. Don't say it goes from 0 to 3,000. Even though that's true, that's not what they're asking. When they ask about intervals, they're talking about the domain. So they're saying from 0 to 25. From 0 to 25. Decreasing. Again, don't look at the 3,000. Here's where it's decreasing. It's decreasing from 50 to 75. Decreasing from 50 to 75. And it's constant in 2 different places. It's constant here and here. And everybody can see, you can get that from the graph, okay? But you're looking at the x numbers, 25 to 50. We'll say this, 25 to 50 unioned with 75 to 100. Notice it doesn't go on to infinity. It stops at 100. And that's it.